Hi, transistors are so mysterious. They are used in almost every circuit board. You may encounter transistors that easily get hot and are destroyed quickly because that transistor is not the right transistor in its place. Choosing the best transistor for a particular application is a challenging task. You have to consider many parameters to do the job perfectly because there are likely tens of thousands, if not hundreds of thousands of different transistor part numbers. Have you ever been confused when you are about to select a transistor to do a simple task or to drive a DC load in your circuit? This video is for you. In this video, I'm going to show you how I choose a specific transistor for a particular application. As a result, I will describe 5 main parameters of transistors to help you find the best transistor for your circuit. The last parameter is the most important, which keeps the transistor cool. Please stay with me until the end of this video. This is a 30-volt DC motor. Suppose that in a project you need to switch this motor through commands from low power sources like microcontrollers or sensors. Since microcontrollers or sensors are operating at low voltages like 5 volts or 3.3 volts, you can connect this motor directly to the GPIO of the microcontroller because the maximum voltage available at microcontroller GPIO is far lower than the operating voltage of this motor. On the other hand, microcontrollers can't provide enough current to drive this motor perfectly. So we need a switch to turn on and off this motor through commands from low power sources like microcontrollers or sensors. There are 2 main approaches, relays or transistors, each of which has its own benefits and drawbacks. I'm not going to discuss the difference between relays and transistors because I have described that in another video. There is a link to that video in the description. On the other hand, transistors are divided into different categories. FET transistors and BJTs are more common. Even though there are similar concepts behind selecting best BJT or selecting best FET, I think it's better to concentrate on one of them. So in this video, I'm going to talk about selecting best BJT, and I hope I could make a similar video about FETs. If you want a similar video about field effect transistors, please let me know in comment section below. Anyway, I'm going to start the discussion by selecting a random transistor. You can search for and choose transistors online on part seller websites or on reference websites like alltransistor.com. I have searched for BJT transistors and found many part numbers, and then I have randomly chosen PD138. Now I'm going to consider main parameters to find the best transistor. The first parameter is parameter number 1, the polarity of the transistor. BJTs fall into 2 main categories, NPNs and PNPs. NPNs are negative transistors and PNPs are positive. In the first step, we have to select right polarity for the transistor. This is a schematic symbol of an NPN transistor, and this one is a PNP. BJTs have 3 terminals: collector, emitter, base, collector, emitter, and base. There is an arrow on emitter terminal, look here and here. The arrow direction is inward in a PNP and it's outward in an NPN transistor. We can use either of them for switching a DC load on and off. Usually an NPN is used to switch ground side or low voltage of the load, and a PNP is used to switch high side of the load. In this case, this motor is running on 30 volts, so high voltage here is 30 volts. If you want to use this circuit, if you want to connect one lead of the motor to ground and switch 30 volts using a PNP, it's possible. You simply need to apply a voltage lower than 29.3 volts to base terminal, which is available at any MCU GPIO. But when you need to stop the motor, you have to apply a voltage higher than 29.3 volts to base terminal, which is not a possible task to be done by a microcontroller. So in this circuit, the microcontroller is not able to turn the motor off. In contrast, NPN transistors are super easy to use and control with a microcontroller. In the circuit, you need to apply a voltage higher than 0.7 volt to base terminal to switch the motor on, and a 0 volt to base terminal to turn the motor off to stop the motor. Both of these voltages are easily produced by microcontroller. It's more suitable to use an NPN type transistor in this case because we are going to switch the motor through commands from a microcontroller. Actually, we can't produce 30 volts on GPIO of a microcontroller to stop the motor. By referring the datasheet, it's clear that the BD138 is a PNP type transistor, so we have to look for an NPN type transistor. Let's search again, this time for an NPN type transistor. There were many results in my first search. I have chosen SS8050, which is an NPN transistor. Why have I selected this transistor, you may ask? There is no specific reason other than the polarity. It's an NPN transistor. Now we have SS8050. The next thing to consider is the motor voltage. Is the motor voltage effective on our choice, you may ask? In this case, the motor voltage is 30 volts. What about 500 volt DC motor? Can any transistor switch any voltage, you may ask? To answer this question, I have to move on to the next parameter. Parameter number 2, collector emitter breakdown voltage. VCEO is one of the most important parameters of any bipolar junction transistor. It indicates the maximum voltage the transistor can withstand on its collector emitter junction. In the circuit, when the transistor is on, the current will go through the motor and the transistor. The motor will drop a large amount of voltage on itself, so the voltage on collector emitter junction will be negligible. But when the transistor is off, the current in this path will be zero, since the load has a known and limited impedance. The load is this DC motor. By using simple Ohm's law, the voltage across the load will be zero and the whole 30 volts will be dropped on the collector emitter junction of this transistor. Why is the voltage not dropped on the load, you may ask? Because it is the transistor that blocks the voltage, not the load. It is the transistor that switches the voltage and has to force the voltage to block the current. As a result, when the transistor is off, the voltage on its collector emitter junction will be 30 volts and the transistor has to withstand this voltage. If you look at the datasheet of this SS8050 transistor, you can find the maximum collector emitter voltage. It's called VCEO. Look here. It's written here that this transistor can withstand 25 volts on its collector emitter junction. So this transistor is not suitable for driving a 30 volt DC motor because it will be destroyed when the transistor is off. Now we have to look for an NPN transistor with VCEO equal to or higher than 30 volts. In my third search, I found 2N3904, which is an NPN transistor and has VCEO equal to 40 volts. 40 volts is higher than 30 volts and it's okay. Let's consider other parameters to see if it is suitable for driving this motor or not. Let's do a simple experiment before going further. This is a 30 volt 2 ampere DC motor. If you apply 30 volts to its terminals, it will start to spin. I'm going to set up the circuit to see how much current it is going to draw. As you see, it's drawing 220 milliamps without load. If I put some load on this motor, using these pliers, it will draw more current. As you see, it is reaching 2 amperes. Based on the information provided by the vendor, this motor will draw up to 2 amperes of current. By looking at this circuit, it's obvious that the 2 ampere is going to pass through the motor and the transistor. So the transistor has to be strong enough to withstand 2 ampere. I know you can guess what the next parameter is. Parameter number 3, collector current or IC. Collector current is the maximum current a transistor can pass through its collector terminal. You can find it on the datasheet by searching for IC. Look here, the collector current of the 2N3904 is 200 milliamps. It's too low for the motor we are going to switch. 200 milliamperes is 10 times lower than 2 amperes. So this transistor is not one we are looking for. If I use this transistor to drive the motor, the transistor will be destroyed immediately. So we have to look for another transistor, this time an NPN transistor with VCEO higher than or equal to 30 volts and collector current higher than or equal to 2 amperes. While I was looking for the right transistor, I came across D882, and guess what? It perfectly met these conditions. I mean, it's an NPN transistor, the VCEO is 30 volts. However, it would be better to choose a transistor with VCEO higher than 30 volts, not exactly equal to 30 volts to have a safety margin, and the collector current equal to 3 amperes. It seems that this transistor fits our needs and it's a suitable choice to drive the motor. To be sure, it's better to check more parameters. Parameter number 4, power dissipation. One thing that I always worry about is the temperature. You know, when transistors switch a load, they get hot, and this phenomenon can easily destroy the component. We have to care about the power dissipation of the device. This is datasheet of D882 transistor. Look here, there's a chart here showing the relation between collector emitter voltage and collector current. Let's suppose that the load is going to draw 2 amperes. So there will be 3 points here where the collector current is equal to 2 amperes. Here, here, and here. This curve shows the collector current versus collector emitter voltage when base current is equal to 8 milliamperes. This curve shows the collector current versus collector emitter voltage when base current is equal to 9 milliamperes. And this curve shows the collector current versus collector emitter voltage when the base current is equal to 10 milliamperes. For each of these points, I mean this point, and this point, we have a collector emitter voltage and a collector current. Since the power dissipation is equal to collector emitter voltage multiplied by collector current, it's easy to calculate the power dissipation for these points. There is a common mistake here when calculating the power dissipation of the transistor. Some beginners calculate the power dissipation of the transistor by multiplying VCC voltage by the load current. This is not correct. This calculation is leading to power dissipation of the load, not the transistor. To get power dissipation of the transistor, you have to multiply VCE, voltage across collector emitter junction of the transistor, by the collector current. The power dissipation here at this point is 4.4 watts, here is 5.8 watts, and here is 10.5 watts. Usually for power dissipations higher than 4 watts, we have to use a heatsink. So for all those 3 points mentioned on the datasheet, we have to use a heatsink. But there is another problem before using a heatsink. There is a parameter on the datasheet called collector power dissipation that determines the maximum power dissipation allowed for the device. The parameter is here. Collector power dissipation is 1.25 watts for this transistor. It's much lower than the power dissipation on these points. Remember, 4.4 watts, 5.8 watts, 10.5 watts. The transistor can't drive this DC motor because of the restriction of the power dissipation. So we have to look for another transistor, this time with these requirements. By a simple search, I had found the TIP41C. It seems to be a good choice. This is datasheet of TIP41C, a power NPN transistor. Let's look at its parameters here at this table. The VCEO of this transistor is 100 volts, which is far higher than 30 volts we need. It is necessary to mention that this parameter shows that we can switch voltages up to 100 volts. It is obvious that voltages lower than 100 volts, like 30 volts, can be switched by this transistor easily. Collector current of this transistor is 6 amperes, which is much higher than 2 ampere we need. Similarly, this parameter indicates maximum collector current. This transistor can switch currents up to 6 amperes, so switching 2 ampere is a piece of cake for this transistor. Maximum power dissipation, or P total dissipation, is 65 watts. Even though I think 65 watts will be enough, but I have to do some calculations to be sure. Let's take a look at figure 6 here. This graph shows collector emitter voltage versus collector current. There are 3 different curves here for different temperatures. If you look attentively here at this point, it's clear that when 2 ampere is passing through the collector, the voltage across the collector emitter junction will be something from 0.15 volts to 0.22 volts. So the power dissipation falls between 0.3 watts and 0.44 watts, which is far less than the 65 watts maximum power dissipation of the device. Wow, we found the best transistor that is suitable for this motor. But no, it's too soon for celebration, because there was another parameter on the graph that I didn't talk about. I mean, this one, the HFE. I know the discussion about power dissipation is not complete yet, but I can't move further without HFE concept, because HFE and power dissipation are interwoven concepts. So now it's better to move on to the next parameter, and we will come back to the power dissipation again. Parameter number 5, DC current gain, or HFE. The HFE shows that how much current a BJT needs on a space terminal to allow the desired current flow into its collector. The HFE is equal to collector current divided by base current. In this graph, the HFE is 10. So to have 2 amperes flowing into the collector, we have to let 200 milliamperes flowing into the base terminal of the transistor. The base current will be really high. The HFE is not a constant value, and it depends on some other parameters like temperature, collector current, collector emitter voltage, etc. But it has minimum and maximum boundaries. The higher the HFE, the higher the power dissipation. I mean, configuring a transistor to operate at its maximum HFE will result in higher power dissipation, and configuring the transistor to operate at a lower HFE will result in lower power dissipation. This is why in this graph we found very low power dissipation, because the HFE is 10, which is very low. In this datasheet there is not the information needed to let me describe the concept clearly, so I'm moving on to another datasheet. Let me mention that there are several datasheets for each part number. They are almost equal, and in most cases they can be used interchangeably. Let me show the figure 8. Where's that? Yeah, it's here. Figure 8 here. The collector emitter voltage versus base current. Look at this chart. If the base current falls below 70 milliamps when the collector current is 2.5 amperes, voltage across the collector emitter junction will drastically increase, resulting in high power dissipation. To have lower collector emitter voltage and consequently low power dissipation, we have to increase the current going into the base terminal. Let me show you another data sheet, this time from Sanyo. Look at this graph here. To have collector current equal to 2 ampere, the base current have to be higher than 40 milliamps. At this point, the HFE is equal to 50, which is relatively high and will result in high power dissipation, which will cause the transistor to get hot. The power dissipation is easily calculable here. The ICE is equal to 2 amperes and the VCE is equal to 5 volts. Then PC will be 10 watts, which is relatively high, and surely it needs a relatively large heatsink. To decrease the HFE and consequently bring down the power dissipation, we need to increase the base current. For example, we need to configure the transistor to operate at this point. At this point, the base current is about 100 milliamps and the VCE is around 1.5 volts. So the power dissipation at this point will be around 3 watts, which is relatively low. In most cases, it can be cooled down by PCB heatsinking and it will not need an external heatsink. If you think that it's over, I have to say no, we are not done yet, because there is a serious problem here. By decreasing the HFE, we have to increase the base current, and the base current has to be supplied by a low power source like microcontroller or a sensor. The GPIO of a microcontroller can provide up to 30 milliamperes of current, not more. So we have to increase the HFE to decrease the base current, and this will cause the transistor to get hot. What we can do? Surprisingly, there is a simple solution for this problem. This is a power NPN transistor, something like TIP41. We have to supply high current to its base terminal to decrease the HFE and consequently decrease the power dissipation of this transistor. But the MCU is not able to provide high currents like 100 milliamps. We can use a small transistor in this way to provide enough current to the base terminal of the larger transistor. In this structure, the total HFE will be the product of first HFE and second HFE. So both of these transistors will be able to operate at lower HFEs. In this example, the MCU has to supply just 5 milliamperes of current to the base terminal of the small transistor. The small transistor is amplifying the 5 milliamperes by HFE1, which is equal to 20. It is going to pass 100 milliamperes to base terminal of the larger transistor. And the larger transistor is amplifying 100 milliampere by HFE2, which is equal to 20. Then the larger transistor will be able to allow 2 amperes of current to pass in peace. This structure is called Darlington pair transistors. In the same condition, Darlington pair transistors will dissipate more power than a single power transistor that is operating at low HFE because of some technical reasons. But when you are going to drive this motor using a single power transistor at high HFE, using Darlington pair transistors will be more wise choice, because Darlington pair transistors offer high HFE and relatively low power dissipation at the same time. It's very important to notice that if you are able to provide high current to base terminal of the transistor, if you are able to configure the transistor to operate at low HFE, using a single power transistor will dissipate lower power than using a Darlington pair. But if you can't configure the transistor to operate at low HFE like this example, using a Darlington pair would be more power efficient. In this case, the motor is drawing 2 amperes and the maximum HFE for TIP41C is 70. So at the HFE equals to 70, we have to provide 28.57 milliamperes to the base terminal. Even though most microcontrollers can provide up to 30 milliamperes of current at their GPIO, using the transistor at this HFE will result in very high power dissipation. In this situation, using a Darlington pair will result in lower power dissipation. The good news is that there are several single package Darlington pair transistors like TIP122 with HFE equal to 1000 or BDW93C with HFE equal to 15,000. You can use them and enjoy high HFE. They are awesome. By the way, these parameters are other parameters that you have to worry about. Furthermore, if you are not familiar with the application of the transistors in the circuit, where in a circuit you have to put a transistor, you can watch this video. Anyway, we have reached the final moments of this video. Thanks for watching. If you enjoyed this video, don't forget to hit the thumbs up button, and if you like this video, make sure to subscribe for more.